You know, it's funny how we treat the number zero. It's like it's the end of the conversation.
It's empty. Nothing there.
Right. A bank account is zero, a test score is zero, and that's it. But in physics, zero can be, well, it can be a little deceptive.
A placeholder for something we just don't understand yet. And that's the perfect theme for today.
It really is. Welcome to our Intellectually Curious series. Today we're doing a deep dive into a paper with a bit of a mouthful for a title.
Just a bit.
It's called Single-Gluon Tree Amplitudes Are Non-Zero.
Seems super technical, I know, but please stick with us on this.
Because our mission here is to unpack how a massive collaboration, we're talking Harvard, Cambridge, OpenAI, proved that a certain particle interaction, one that physicists basically ignored for decades because they assumed it was impossible.
Assumed it was zero.
Exactly. They proved it actually exists, and the way they proved it is the real story here.
Oh, yeah. The kicker is that humans didn't find the math, and AI did.
Which is the part that, it genuinely blew my mind. But before we get to our new robot physicist overlords, we should probably set the stage.
Right. We have to talk about scattering amplitudes.
So in simple terms, what are we talking about?
Think of them as the source code for quantum probabilities. You smash particles together, and you want to know the chances of what comes out. That's the amplitude.
And usually we'd map that with those little squiggly drawings, the Feynman diagrams.
Exactly. But here's the problem with those diagrams. They are wildly inefficient.
As you add more particles, the complexity it explodes.
It grows faster than exponentially. It becomes a computational nightmare. So physicists are always looking for shortcuts or for configurations that just, cancel out to zero.
So they can ignore them.
Right. And that's what everyone thought happened with these single minus amplitudes.
Okay, so gluons have this property, helicity, which is basically their spin.
And the assumption for decades was if you have a bunch of gluons spinning one way plus and just a single one spinning the other way minus, the math just, poof, it vanishes.
It goes to zero. So why look for something in an empty cup?
But this paper says, hold on. If you arrange the particles in a very, very specific geometric alignment, they call it a half-collinear configuration, the math doesn't vanish.
Half-collinear sounds complicated.
It's just about the angle you look from. Think of it like a chaotic sculpture. From most angles, it's a mess. But from one precise spot, it all aligns into a perfect shape. That's the idea. The interaction isn't zero. It's just very specific.
Finding that perfect shape, though, that requires massive, massive computational power.
Just a staggering amount.
And that, brings us to our sponsor, Embersilk. Because if you're listening and thinking about that kind of heavy lifting for your own business, whether it's AI training, automation, or software integration, Embersilk is who you talk to.
They're experts at finding out where intelligent agents can make the biggest impact for you.
They really are. Check them out at embersilk.com. Okay, so we have this special setup, this half-collinear thing, where the physics doesn't just disappear.
Right, but the math to describe it is notoriously hard.
And this is where the story gets really, really weird.
This is my favorite part. The authors didn't derive the key formula, equation 39, themselves. It was conjectured by GPT 5.2 Pro.
I just want to pause on that for a second. We're not saying the AI summarized an article.
No.
We're saying it looked at raw numerical data and intuited a fundamental physics formula that humans hadn't seen.
That's exactly what happened. They fed it the data, and it spotted a pattern and just spit out this beautiful closed-form expression.
And it wasn't a mess, right? It was elegant.
Incredibly elegant. It used something called piecewise-constant integers.
Which is math speak for saying the answer comes in simple whole number steps, not some messy curve.
Precisely. It was so clean the humans were skeptical, but they checked it. An internal OpenAI model proved it first, and then the researchers verified it by hand using a method called Baron-Geel recursion.
So the AI was right.
It was dead on. And this matters because it bridges this huge gap in what's called self-dual Yang-Mills theory. It connects the simple diagrams to the really complex classical theory.
It's like finding a missing evolutionary link.
It is. And it's robust. The formula works. It satisfies all the big checks like Weinberg's soft theorem. It plays by the rules of the universe.
That's the optimistic takeaway for me. This isn't just about AI writing emails. We're using it to extend our own theoretical reach, to see things we couldn't before.
It feels like a new kind of partnership. Human theory guiding AI intuition. And that intuition spotting patterns were too close to the problem to see.
It's a glimpse into a future where we might actually solve some of these huge unsolvable problems together.
I think so.
So I guess here's a thought to leave you with. If an AI can look at a pile of things we all thought were zero and find a hidden key to how the universe works.
Hmm.
What other fundamental assumptions are we holding on to right now that are just waiting to be proven wrong?
It's a thrilling question to be asking.
It really is. Thanks for diving in with us. If you enjoyed this, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out.
Thanks for tuning in.